This unit focuses on another route for synthesizing alcohol products, and here we're going to focus on our starting material for the reaction being a deprotonated alkyne that we will use as a nucleophile to enable the synthesis of alcohol products. Let's take a look at this. When we think about deprotonated alkynes, that is a throwback to our units on alkynes, where we talked about one of the reactions of alkynes was that we could take a terminal alkyne, treat it with a really strong base, and create a deprotonated alkyne that is useful as a nucleophile. So that reaction was that we would start with an alkyne, and it had to be a terminal alkyne. So in other words, it had to be an alkyne that had a hydrogen directly bonded to that sp carbon, because the sp carbon is more acidic, meaning it's more easily deprotonated than alkene or alkane carbons. And what we would do is treat that with a super strong base. And for a super strong base, we were using typically things that had nitrogen anions, such as sodium amide would have a nitrogen anion, or lithium diisopropyl amide would also qualify for that. And what would happen there is that that strong base would create a favorable equilibrium for deprotonation of the alkyne. So the base, such as our nitrogen anion, which I'll just put an R group there to make it generic, would come in, grab a proton from our acid, our alkyne, forcing the carbon-hydrogen bond to break, and giving us our deprotonated alkyne as our product here with a lone pair of electrons and a negative formal charge. So looking at that, we would recognize this as a nucleophile because it has a lone pair of electrons and that negative formal charge, which is going to make it a very good nucleophile. It also itself would actually be a really strong base as well. But if we take that nucleophile and mix it with a source of electrophilic carbon atom, it's going to be able to act as a nucleophile to react. And so previously what we saw was that we could take that deprotonated alkyne nucleophile and we could react it with a molecule that had a good leaving group bonded to it, such as an alkyl halide. So we could take it and react with something like CH3CH2Cl and do an SN2 type reaction where the deprotonated alkyne is the nucleophile, our source of electrons, that attacks the electrophilic carbon. That's the carbon that's bonded to an electronegative atom, because that carbon that we're attacking there is positively polarized. And at the same time that that's happening, the leaving group leaves to avoid the carbon going over the octet rule. And that would effectively create a new carbon-carbon bond, which would make this reaction really, really valuable in terms of creating complicated products out of simple starting materials. So we go ahead and draw out our full product for that in this reaction that we've seen previously. Now, as we extend this theme further and we want to try to use our nucleophilic deprotonated alkyne as a source, or a resource rather, for creating alcohol products, what we can do is mix up the identity of the electrophilic carbon so that we'll be able to yield an alcohol product. So let's take a look at this now in a little bit more detail to show you what I mean. So we're going to look at the use of deprotonated alkynes to yield alcohols. So we'll take our deprotonated alkyne that we had created up top there, which is just our generic R group, bonded to a terminal deprotonated alkyne, like so. And if we mix that alkyne with, let's do an epoxide, that is, remember, a three-membered ring, where one of the atoms in the ring is an alcohol, is an oxygen atom. What's going to happen here is that we would expect that each of the two carbon atoms here and here are quite positively polarized, because that oxygen atom is electronegative, so it's drawing electron density away from those carbons, making those carbons electrophilic. And so what will happen is that the nucleophile is going to be very, very drawn to those. So the nucleophile lone pair electrons come over, attack this carbon, and that process is made particularly favorable because the three-membered ring is relatively strained. And so when the nucleophile attacks there, this bond connecting the carbon and oxygen is especially eager to break, because that's going to release the angle strain of the molecule. We can then go ahead and draw what product would result from this. So the product resulting from this, we'll go ahead and plug in what began as our alkyne. And then the lone pair electrons on the alkyne became a covalent bond to the carbon that was positively polarized there. So I'll go ahead and put that carbon in red. That was this carbon right here. This carbon of the epoxide is still connected to the one it was next door to, so I'm going to go ahead and draw that one that was next door in as well. And this carbon here on the left was actually a CH2 group to fill its octet, so we'll go ahead and fill in the CH2. We come over to the next carbon, and the next carbon is also a CH2, so we go ahead and fill in the CH2 there. And then that carbon is going to remain at this point bonded to the oxygen atom because we didn't show any bonds breaking on that side. So we'll go ahead and plug in the oxygen atom there, and that oxygen had 2 sets of lone pairs to start with. It picked up a 3rd set of lone pairs by breaking the carbon-oxygen bond right here, and so therefore it will have an extra lone pair there and hence a negative formal charge. So now at this point we're pretty close to having created an alcohol molecule. What we would need to do is protonate that oxygen. And in order to protonate that oxygen, we will have to add something else to the reaction mixture, because if you look at what's available at the moment, we just have an alkyne plus an epoxide. We don't have any source of proton available there. And so what we would need to do here is bring in acid in order to allow that protonation to take place. So lone pair electron comes over, attacks the proton, leading us to our final observed alcohol product out of this reaction. So we're going to fill that in like so, giving us our alcohol product. So the advantage that we see here is that due to the fact that we're using a deprotonated alkyne as a carbon-based nucleophile, we're not only creating an alcohol product out of this reaction, we're also creating a new carbon-carbon bond. That was the bond that we were showing right here is newly formed. So we're making a molecule that's more complex and also that has an alcohol functional group in it. This is super useful because we can then do a lot of different reactions of either the alkyne group to change this molecule around some more, or the hydroxy group to alter this molecule some more to make compounds that would have a targeted practical application. So another way to take a deprotonated alkyne and use that as a tool for yielding alcohol products is, rather than using an epoxide with your deprotonated alkyne, instead we could use an aldehyde or ketone with the deprotonated alkyne. So let's take a look at that scenario right here. So we'll take our same starting material, deprotonated alkyne. We'll react it now with an aldehyde or ketone. So let's go ahead and do acetone, also relatively commonly known as fingernail polish remover. And in the acetone molecule, much like the epoxide, we have a very positively polarized carbon atom right here that's bonded to that electronegative oxygen. And that positive polarization we can take advantage of by having our nucleophile come over, being very attracted to it. It forms a bond here. And the fact that we have a pi bond connecting to the oxygen is to our benefit because we can readily move the electrons from that pi bond up onto the oxygen. Pi bonds tend to be very easily mobile, so we'll go ahead and do that to create our intermediate. Our product that results from this is going to correspond to having our alkyne now linked with the bond I'll show in red to that middle carbon, the electrophilic carbon from our ketone. So the electrophilic carbon from the ketone shown in red here, and then the 2 methyl groups it's bonded to, I'm just going to put here and here, so 2 CH3 groups at the ends of that, what was our ketone molecule, and then that carbon is also bonded to an oxygen now, connected with a single bond to that oxygen because the pi bond went up onto the oxygen, and therefore that oxygen has a negative formal charge. Now at this point, the molecule that we're looking at is very analogous to the one we saw just above when we did this reaction with the epoxide, and then we have an oxygen anion within the molecule. So all we need to do now is, after this reaction is completely taken place, acidify the reaction mixture to enable protonation to take place. So for the protonation to take place, we take our lone pair of electrons from here, bring that down with our electron pushing arrow to form a bond to our proton, and we'll go ahead and draw out our final product resulting from this. So we go ahead and draw all of this out. Our OH group now in place, and we are good to go with this. In this reaction, just like when we did the reaction with the epoxide, we've created a new carbon-carbon bond in this reaction and also implemented an alcohol group. We can do the same type of reaction using, rather than a ketone, we can also use an aldehyde for this. So let's go ahead and show that process happening as well. So we start with our alkyne that's been deprotonated, react it this time with an aldehyde, and that's going to lead us through the same type of pathway here, where we expect that the nucleophilic carbon is going to come over, attack the electrophilic carbon right here. That forces the carbon-oxygen bond electrons to go up onto the oxygen, and we'll go ahead and draw out the intermediate that would result from this. I'll draw the new bond in red, and then I'll draw the atoms that originated from our aldehyde in blue. So our aldehyde carbonyl carbon is right here in blue. That carbonyl carbon is no longer connected to a carbonyl. Instead, it's linked by a single bond to an oxygen that's going to be an oxygen anion. It's also directly connected to a hydrogen, which I'll just put down here, and directly connected to that methyl group. So now we have very close to our final product. At this point, we would implement a second step of the reaction, where we would bring in a source of proton, a source of acid in other words, to get the protonation going on of that oxygen to give us our final alcohol product that we would observe in our reaction flask. So let's go ahead and show that final product here. Like so. So that's going to be that. You will notice here in this particular reaction product that we have created a chiral center in our final product. Our final product has a chiral center right here. So we should ask ourselves whether we would expect that to be specifically an R chiral center, an S chiral center, or a racemic mixture of both. To establish that, we need to look at the point in the mechanism where the chiral center was formed. So the chiral center was formed at this step right here, where we took our nucleophile and we attacked our carbonyl carbon in order to create a chiral center. The chiral center is first observed right here. So we need to ask ourselves what the stereochemistry constraints are of this attack of the nucleophile on the carbonyl. The carbonyl, if we think about the molecular shape at this carbon, the molecular shape there, since we have a carbon that has 3 regions of electron density, is trigonal planar. Since it's trigonal planar, that means that the nucleophile can attack it either from the top face or the bottom face. Since it's a plane, it doesn't matter which face it attacks from. And therefore, that will lead to a mixture of the R and S products, since the attack of the nucleophile can be either from the top face or the bottom face of the molecule. So the actual stereochemistry at this carbon is going to be a racemic mixture of R and S enantiomers there. And so you should be comfortable with doing such things as drawing the wedge and the dash there to show that the actual product, if we were looking at stereochemistry, would be a mixture of the R and the S products. Now keep in mind, when you are trying to synthesize alcohols using a deprotonated alkyne, that it is important that we specify when we are adding each reagent to the reaction mixture. What I mean there is that if rather than writing out a full mechanism, you were just writing out the reaction, what you would need to do is indicate that you have to add the reagents in order. That first, you would take your deprotonated alkyne, or we could even start from the protonated alkyne, like so. Indicate that first you would treat that with base to deprotonate it, so I'm putting LDA in as my base. After that reaction had totally finished, then secondly, you would add your source of electrophilic carbon that's bonded to an oxygen. So you add your source of, say, our epoxide or our ketone or aldehyde. And then thirdly, after that reaction had totally taken place, that's when you would have to add the acid. So using the numbers here indicates that you're not adding all three of those reagents simultaneously. Instead, you're adding them in order, one after the other, which is absolutely essential for this reaction to take place properly. Because if you were to take all three of these and just mix them all in at once, well, for one, the base from step 1 and the acid from step 3 would just quickly react with one another and neutralize, and nothing would happen. So it's absolutely essential that you put these in order. So you might come into a situation where you see a reaction written out like we've put down here at the bottom, and you're just asked to provide the final product for the reaction. If that's the case, you can use certainly your mechanistic steps to help you along the way, but what you need to put in the end scenario is just the final reaction product or products. So thinking about this particular example problem and working through this, I encourage you to hit pause and see if you can get to the final product on your own to test how well you're doing with these concepts. When I look at the answer to this, what we will do is first we're going to say what the product is of step 1. The product of step 1 is going to be the deprotonated alkyne. So I'm just going to put in my deprotonated alkyne. That's what's going to feed into step 2. So in step 2, what will happen here is that we will have our epoxide reacting with our deprotonated alkyne nucleophile, like so, giving way to the intermediate that results from that. So in this case, we have here 2 electrophilic carbons, here and here. So we need to ask which one of those is going to be attacked by our carb anion. We can think of this reaction as being an SN2 type reaction because the nucleophile is going to attack one of those 2 carbon atoms at the same time that the leaving group, the oxygen, breaks away. And so SN2 reactions favor a less sterically hindered electrophile. In other words, a less substituted electrophile. So if we're favoring a less sterically hindered carbon electrophile, and we look at the 2 carbons here and here as our 2 electrophile candidates, definitely the one on the left is less sterically hindered. It's the less substituted carbons. Those fewer alkyl groups are going to mean that it's easier for that nucleophile to get in an attack. At the same time, the leaving group breaks away. So we'll go ahead and draw out the product that would result from that. And keeping in mind that this is a general rule where if you have an anionic nucleophile, it's going to attack the less sterically hindered of the 2 epoxide atoms. The more sterically hindered the epoxide atoms are, the slower this reaction will take place. Let's go ahead and draw out our product resulting from this. So we have what we started with is our deprotonated alkyne. Now it's formed a covalent bond, which I'll show in blue, over to the epoxide, and then I'm going to show the what was originally the epoxide in black here. So the attack was on a CH2 group from the epoxide. That was that CH2 right here on the left that I'm putting a black dot on. That CH2 group was bonded to the next carbon atom that's to its right that I have a red dot on. That red dot carbon atom was bonded directly to a methyl group. Actually, it's bonded to 2 methyl groups, so I can just plug this in as CH3 and then put a subscript 2 there. And then the other thing to remember is that that carbon is also going to be bonded to your oxygen atom. That oxygen will have 3 sets of lone pair electrons to give it a negative formal charge for now. So this is going to be the product that results from step 2 of the reaction. Then step 3 of the reaction is the final reaction of this series. It's going to lead us to the final product that we need to put into that pink box up top. So step 3 is just a protonation step. Since we're adding acid, so we have an oxygen anion. And going into step 3, that oxygen is going to pick up the proton to give us our final product here. So if you're given a reaction sequence like this and asked what the major organic product would be of the reaction, you don't have to show all the steps along the way. Make your life easy. Don't make your life harder than it needs to be. Just go ahead and work through your scratch paper of how to get to the final product, and then plug the final product in to the box here. And then the other thing that you can ask yourself here, and should ask yourself here, is this a chiral center that we've just created? The answer in this case is no, it's not a chiral center. If it was a chiral center, we would need to show both the R and the S forms, but it's not, so we can leave it as is. So with this, hopefully what you've learned here is that you can use deprotonated alkynes as resources for making both new carbon-carbon bonds and creating alcohol products as long as you have that deprotonated alkyne attacking either the carbonyl group of an aldehyde or ketone or attacking an epoxide molecule to break open the epoxide ring. In the next segment, we're going to look at some additional ways to create alcohols using nucleophiles that are carbon atoms.